In the previous slide, we indicated that since Coulombic interactions between ions occur even when the ions are separated by large distances, we need to account for deviations from ideal dilute solution behavior for electrolyte solutions, even when they are very dilute. Hence, we must determine the activity coefficients for the solutes. We first need to recognize that any electrolyte dissolved in water yields two ionic species, a cation and an anion. So we need to define an activity coefficient gamma plus for the cation and an activity coefficient gamma minus for the anion. However, we know that we cannot isolate the cations from the anions in a solution. Indeed, in a given solution, any given anion repels other anions and attracts cations. Similarly, any cation repels other cations and attracts anions. Hence, we cannot estimate separately the deviations from ideal solution behavior associated with the cations and these associated with the anions. As a consequence, we will not attempt to use activity coefficients for the individual anions and cations, but we will define a mean activity coefficient called gamma plus minus for a given electrolyte dissociated in aqueous solution. From Coulomb's law, we anticipate that the electrostatic interactions will be a function of the charges of both the cation and the anion that make up the electrolyte. Hence, the expression for the mean activity coefficient should reflect the importance of ionic charges. Over the next two slides, we will demonstrate that for a salt of formula unit MPXQ, the mean activity coefficient, gamma plus minus, is obtained by raising to the power 1 over S the product of gamma plus raised to the power P and gamma minus raised to the power Q, where S is the sum P plus Q.